Good morning everyone. So we have our next lecture, which is a special lecture based on basics of Laplace transform on the subject, that is basic signals and systems, and this lecture is basically for EN second year. And in this lecture we are see the Laplace transform properties and how we can convert a particular signal into a frequency domain with the help of Laplace transform. So, motivation behind the Laplace transform. Another important mathematical tool in the study of signals and systems is known as Laplace transform. The Laplace transform can be viewed as a generalization of the Fourier transform. So, as we have not discussed about Fourier transform, but we can have a glimpse of Fourier transform also in this lecture. Due to its more general nature, the Laplace transform has a number of advantages over the Fourier transform. Or we can say that in Fourier transform, we don't have a detailed analysis of the signal, but in Laplace transform, we can have a detailed analysis of the signal by checking whether a signal is stable, causal or not. First, the Laplace transform representation exists for some signals that do not have Fourier transform representation. So, we can handle a larger class of signal with the help of the Laplace transform. Second, since the Laplace transform is a more general tool, it can provide additional insights, as I have told you, beyond those facilitated by the Fourier transform. So, in the Fourier transform, we do not have region of convergence, which is present in the Laplace transform. We do not have to check. We do not have the idea to check the signal is causal or stable in the case of the Fourier transform. But in the case of the Laplace transform, we can check these properties of the signals also. So, motivation behind reading this Laplace transform, that in particularly for LTI system, that is linear time invariant system, which has a system H with impulse response H, we have a formula that is H of e to the power st, that is equivalent to Hs e to the power st, where Hs is equivalent to minus infinity to infinity H of t e to the power minus st dt. Previously, we referred to H as the system function. As it turns out, H is the Laplace transform of small h. Since the Laplace transform has already appeared in the context of the LTI system, it is clearly a useful tool. Further, as we will see, the Laplace transform has many additional uses in the later slides. So, we just start with the bilateral Laplace transform. So, the formula for bilateral Laplace transform of the function xt can be represented as x of s. So, in Laplace transform, we generally use S domain. So, the formula is from minus infinity to infinity xt e to the power minus st dt. The inverse Laplace transform of x is, or we can have xt, which is inverse Laplace transform of xs, and this can be represented as 1 upon 2 pi j, that is from minus infinity or sigma minus j infinity to sigma plus j infinity xs e to the power st ds. Also in the S domain, we have two parts, one is real part and another one is the imaginary part. So, S have two categories, that is real and imaginary. On the other hand, in Fourier, we have only imaginary part, j omega part. In that case, in Fourier, we have sigma equivalent to 0. So, by this way, you can see that in the place of S, we can have j omega in the case of the Fourier. The inverse Laplace transform we perform by using partial fraction method, not by using this formula, sigma. So, we have a ROC region, which is real of S and imaginary of S. So, real of S is sigma, imaginary of S is j omega, and we see the points which are valid on this region of convergence for which the Laplace transform is existing. So, we refer to x and capital X as a Laplace transform pair. So, we can write like this: xt, Laplace transform of xt is defined by xs, or inverse of xs is defined by xt. In practice, we do not usually compute inverse Laplace transform by directly using the formula from above, and instead we just use the partial fraction method, which we will discuss in the later slide. So, bilateral and unilateral Laplace transform. So, when we say bilateral Laplace transform, it is from minus infinity to infinity, or you can say two-sided Laplace transform. But unilateral Laplace transform, that is from one-sided, that is either from minus infinity to 0 or from 0 to infinity. As it turns out, the only difference between the definitions of the bilateral and unilateral Laplace transform is the lower limit of the integration. So, in first case, we have from minus infinity to infinity, in the other case, it is from 0 to infinity. So what is the relationship between Laplace transform and Fourier transform? So as I have told you that Laplace transform can be, or Fourier transform can be easily written in terms of Laplace transform if we put only sigma is equivalent to 0 in the S domain. So if we take S domain sigma equivalent to 0, the Laplace transform part is automatically converted into a Fourier transform. So suppose let X and XF denote the Laplace transform and CTFT of capital X respectively, and then the function XS evaluated at S is equivalent to j omega, where omega is real, can be written as XS is equivalent to XF of omega. But here we are taking just sigma is equivalent to 0 in the case of the Laplace transform. Due to the preceding relationship, the Fourier transform of X is sometimes written as X of j omega also. The function X is evaluated at any arbitrary complex value, that is S is equivalent to sigma plus j omega, where sigma is equivalent to real value of S and omega is imaginary value of S, can be also expressed in terms of Fourier transform involving X. But we have to see that when XS is equivalent to S plus sigma plus j omega, it truly comes out to be XF of omega only when we take sigma equivalent to 0, which we have discussed in the earlier slide. So if we have a question that find the Laplace transform of the function where a is a real constant and this function is basically a exponentially decaying function, that is xt is equivalent to e to the power minus at ut. So from the definition of the Laplace transform, we just have ut is equivalent to 1 for t greater than 0 and 0 for t less than 0. So we know that the lower limit is from 0 to infinity in the case of when any signal is multiplied with ut. So here just we transform Laplace of e to the power minus at ut, e to the power minus at ut, e to the power minus st dt. But in the case of ut, we just put 1 and the limit will change from 0 to infinity. By solving this, you just get 1 upon s plus a, which is your xs. Laplace transform. Now we have to find out whether what is the ROC of this Laplace transform. So ROC is defined by those points in the S domain for which the Laplace transform is existing or is valid. So you can see that when s equivalent to minus a, the function becomes infinity, because minus a plus a becomes 0 and 1 upon 0 becomes infinity. So we don't have the ROC at s equivalent to minus a. Either it can be s greater than minus a, or real of s greater than minus a, or real of s less than minus a. So how to decide the ROC is real of s greater than minus a or real of s less than minus a? Also, the ROC always exists in terms of real values of the s, not with imaginary values of s, or we cannot compare s greater than minus a, because if we are comparing s greater than minus a, it contains both the real and imaginary part. So we have to write specifically that real of s greater than minus a. So when you see the question, it has a unit step function in the multiplied with a signal. So when you multiply a signal with unit step function, it will automatically come towards the right side only. So when there will be a right-sided, purely right-sided signal, then the ROC will be denominator greater than equivalent to 0, or you can say real of s greater than equivalent to minus a. If the function is u of minus t, suppose in this question we have xt is equivalent to e to the power minus at u of minus t, and the function have the Laplace transform, when you calculate it, it becomes minus of 1 upon s plus a. So the function have the value minus 1 upon s plus a. Also, if you take minus of e to the power minus at, then it becomes 1 upon s plus a. So for both the function, we have the same Laplace transform, but the ROC in the first case is real of s greater than minus a due to this ut term, and in the other case, it will be real of s less than minus a due to this u of minus t term, because this is a left-sided signal, and the signal now becomes purely left-sided, for which you are just calculating your Laplace transform. So you have to careful about whether the signal is right-sided signal or left-sided. If it is right, then the ROC will be the right half plane, right of the rightmost pole, and if it is left, then it will be left of the leftmost pole. So here we have just visualizing this, that 1 upon s plus a, and the ROC is real of s greater than minus a. Next question we have, find the Laplace transform. Similarly, we can find out the Laplace transform as we have discussed, minus of e to the power minus at, u of minus t. You will get the same function, that is 1 upon s plus a, but the ROC is real of s less than minus a. That is the grey shaded region. Next question, find the Laplace transform of the function that is xt is equivalent to ut. Ut is the unit step function. So for unit step function, the integration limit is from 0 to infinity. In place of ut, we just write 1 into e to the power minus st dt. And when you calculate, then Laplace transform of ut, which is us, is 1 upon s. So when you take s equivalent to 0, this function becomes infinity. So we have the ROC, that is real of s greater than 0. So this is the ROC for ut. So you can see 1 upon s and ut 1 upon s, and for ROC is the real of s greater than 0. Now we just have an idea of the region of convergence for the Laplace transform. So let R denote a set in the complex plane A, set R comprised of all complex number s such that real of s is less than a. For some real constant is said to be a left half plane, that is LHP you can say, and for real of s greater than a, for some real constant a is said to be right half plane. So you can say, you can see from the figure also that a is the pole, and we are just drawing, it must be minus a. We are just drawing real of s less than minus a, and less than minus a is basically left half plane, and then in the case of the real of s greater than a, it is right half plane, and that is basically a right half plane, or real of s greater than a. It can be also, it can be minus a, or it can be minus a and a. This is 0 basically. This line is showing 0, 0 and 0. So according to this, you can see that it is minus a, it is a, and then 0 above 0 is a, and below 0 is minus a. So below minus a, that is real of s less than minus a. This is real of s less than a. Again real of s greater than minus a, and real of s greater than a. So these are 4 conditions for which we are deciding whether it is in the left half plane or it is in the right half plane. So in this lecture, we are just covering what we have done in the Laplace transform, that we have to just see whether there is a right half plane or left half plane in the function. And you can see in the figure also, or you can solve some numericals on this topic particularly, that for example xt is equivalent to del t. So this is particularly a impulse function which we have discussed in the first lecture. So impulse function, you can solve that del t is equivalent to 1 for t equivalent to 0, or we have minus infinity to infinity del t dt, that is equivalent to 1 at t equivalent to 0, and elsewhere it is 0. So if you want to find out the Laplace transform of del t, you have to see the basic formula, that is xs is equivalent to minus infinity to infinity del t e to the power minus st and dt. As we know, minus infinity to infinity del t dt is equivalent to 1 for t equivalent to 0. If you put this, that it becomes minus infinity to infinity del t e to the power minus st dt at t equivalent to 0, and we have e to the power minus st dt at, e to the power minus st at t equivalent to 0, and it becomes 1. So we can say that various numericals based on this basic formula or the classical formula of Laplace transform, you can solve for various categories of signal. Either it can be a unit step function, it can be a impulse function, it can be a ramp function, these type of, or sinusoidal sin omega naught t ut. Similarly, cosinusoidal cos omega naught t ut. So you can solve for these functions the Laplace transform, and you can calculate the ROC region of convergence for particularly of these signals. You can have you can have the value of ROC, or the ROC you can define here because its value is 1. So the ROC in the case of the impulse function is entire S domain or S plane, you can say, or entire S plane. Similarly, for cos and sine, you can calculate the value of the Laplace transform. In the case of the cos function or the sine function, suppose xt is equivalent to cos omega naught t ut, then you have to firstly break into exponential functions, e to the power minus j omega naught t plus e to the power j omega naught t divided by 2. Then we have to find out the Laplace transform and multiplied by ut. So you have to find out the Laplace transform, that is Laplace transform of xt, that is half of Laplace transform of e to the power j omega naught t ut, and plus half of Laplace transform of e to the power minus j omega naught t ut, like this. And as we know, e to the power minus at ut, Laplace transform of this is 1 upon s plus a. Similarly, we can put 1 upon 2, and for this 1 upon s minus j omega naught, and plus 1 upon 2 and 1 upon s plus j omega naught. So as we see, there are no real terms in the denominator part on comparison with s. So we have the ROC. If you see the ROC from this expression only, that is real of s is greater than 0. If there is no real part, then we write an important point, then we write ROC is real of s greater than 0. When you solve this, 1 upon s plus j omega naught plus s minus j omega naught upon s square plus omega naught square, because j square is equivalent to minus 1. So it will be cut down, then 2s upon s square plus omega naught square multiplied by 2, 2 also cut, and then s upon s square plus omega naught square. So by this way you can have the formula for cos, or we have for the xt is equivalent to, for xt is equivalent to cos omega naught t ut, and for this x is equivalent to, it comes out to be s square plus omega naught square, and ROC we defined here like in the above part or in the above step. From that step only you can define the ROC, which is real of s greater than 0, as there is no real part in the function. Similarly, for sine omega naught t, these are very common sequences. You can find out the Laplace transform easily for these functions. For sine omega naught t ut, Laplace transform of sine omega naught t ut, you can find that comes out to be omega naught upon s square plus omega naught square, and again the ROC is real of s is greater than 0 for sine omega naught t and ut. So these are some common sequences, they like unit step function, ramp function, impulse function, sine omega naught t ut, cos omega naught t ut. By the help of particular basic formula, that is xs is equivalent to minus infinity to infinity xt e to the power minus st dt, you can find out the values of particular these functions. Similarly, we have different properties of the Laplace transform on which we also solve these type of problems. So the properties are, you can name it, there are numerous properties like around 11 to 13 properties. Firstly, it is linearity, then time shifting, then frequency shifting, differentiation in time, differentiation in frequency, convolution theorem, multiplication property, conjugation property, and then initial and final value theorem for the Laplace transform. So these properties also With the help of these property, you can solve various kind of numericals, like the first, which is we have discussed, that is sine and cosine, that is sine omega naught t and cosine omega naught t. This based on linearity property. So in the later lecture of the lecture number 3, we just discuss about the properties of the Laplace transform. So these two numerical problems are based on linearity property of the particular Laplace transform. As we have discussed in our first lecture, the linearity property is basically which holds both the properties, that is superposition and homogeneity. So in superposition, we just add both the signals x1t and x2t, and in homogeneity, we just multiply with some scaling factor, that is a1 x1t plus a2 x2t, and it will give you the in the Laplace domain a1 x1 s plus a2 x2 s. So by this you can see from the example also that 1 by 2 factor and 1 by 2 factor is a1 and a2. So a1 and a2, a1 x1 s plus a2 x2 s you are getting in the output. So we have with the help of those properties, we can also solve these basic numericals. So firstly, you have to see the classical method of the solving these numericals, and then the advanced method is based on the properties of the Laplace transform. So thank you so much. In the next lecture, we will discuss the properties and then the differential equation, solving differential equations using Laplace transform, and then stability and causality of the Laplace transform. How to see from the ROC itself, the function is stable and causal. Thank you so much.